Thank you, Grayson. Our last presentation is Roman Decca from ICE 911. I'm somewhat ambivalent as to whether this is a hopeful presentation for our future or a depressing statement on our failure to act in the past. Regardless, I think we'd all like to see more ice in the Arctic at this point. And in the spirit of yesterday's election, I think it's safe to say, based on my very unscientific polling, that 100% of polar bears agree with that sentiment. So here you go, Roman.
Behind me, you'll see an ad from 1962. Humble Oil was actually bragging about how much ice they could melt. Well, fast forward to 2018, and it's not so funny anymore. We've actually lost 80% of ice in the Arctic. And what's worse, the ice that's coming back each year is thin, transparent first-year ice, which doesn't reflect nearly as much solar radiation. This is leading to approximately 1/3 of temperature rise when you account for the change in reflectivity. And why that is because the multi-year ice that's been lost was 80% reflective. The first-year ice that comes back is 30% reflective. And what's worse, the open ocean that's being exposed is only 5% reflective. So think of all the heat that's being absorbed. And what that amounts to in real people speak is that for every 2 molecules of carbon dioxide emitted, 1/3 is essentially emitted from Arctic ice loss. And what that also means is that the Arctic is the biggest lever on climate change that we can pull to make an impact before it's too late. The Arctic is also influencing extreme weather directly. Wildfires in California, nor'easter storms on the east, and it triggers permafrost melt. Permafrost contains double the carbon dioxide of the atmosphere. So if we want to do something about permafrost, we attack the Arctic. By 2030, climate modelers are projecting an ice-free Arctic, and that could be really deleterious. And then by 2050, 1 billion climate refugees if we don't change our current climate trajectory. So here comes ICE 911 research. It was founded by a Stanford professor and inventor, Dr. Leslie Field, and it was founded as a nonprofit with the first principle, do no harm. So how do you do no harm while restoring Arctic ice with a material solution? Well, you use silica. Silica is the most ubiquitous element probably on this planet. It is the main constituent of 95% of rocks. It's harmless to wildlife and ecosystems because we've co-evolved with it. It's already being produced and it's low cost. And all you need is a thin layer of it on top of that first-year transparent ice to get it to act like multi-year ice. And on a climatic scale, that can make a huge impact. How do we actually test this hypothesis? First, we deploy the material in the Arctic. Second, we monitor our test sites from our lab in California. And third, we do climate modeling with the data that we get from the test site and see how we can have an impact on a broader scale. This bottom photo shows how much brighter the material is on top of bare ice. And the top photo shows the same pond later in the season with the left side where we applied material and the right side as a control. As you can see, there's a massive difference. And on a climatic scale, that's even bigger. Here's the Big Kahuna. This is our Arctic test site in Barrow, Alaska. We deployed 2 football fields of material here this year, and we monitored it with those 2 buoys that use satellite connection to get data back to our lab in the bay. And then we used that data in our climate modeling. This is a thought experiment where we said, over 40 years of application, on the right side, you'll see the ICE 911 solution and business as usual after 40 years. That difference is massive. But we don't want to coat the whole Arctic. We want to go for the Beaufort Gyre, which is where young ice forms but doesn't survive to become multi-year ice, and then the Fram Strait, which is where ice flows out in the winter, ice flows out in the summer. And how you do this is you use a ship. You use 3 ships for an area the size of Belgium. You target newly forming ice. What people don't know is that ice in the Arctic forms from the bottom. So if you get the top layer of the newly forming ice, you can help that first-year ice survive to become multi-year ice. So the ICE 911 solution is low cost, it's scalable, it's localized and reversible because it's strategic, and it's restorative, most importantly. You're restoring reflectivity in an area that used to be reflective, not doing it somewhere else that didn't used to be. So we're going to scale our testing from lake ice to sea ice. Then we're going to scale up that sea ice testing. And in parallel, we'll do climate modeling. And by 2022, we want to be at a 1% full-scale deployment in the Beaufort Gyre or the Fram Strait. What we need to do that is $5 to $10 million a year for the next 3 years for climate modeling, more governance work, and scaling that actual sea ice testing and working with the ship that we want to work with. So what are the relative costs here? Well, just the debris removal from the Sonoma fires cost $1 billion. Superstorm Sandy's cleanup cost $65 billion. ICE 911 scale up, we're asking for $5 million, and then at full scale, it's less than $1 billion a year for application, and you stop after a period of time. Without doing something in the Arctic, we're going to be stuck in this climate loop of rising temperatures, more extreme weather, shrinking sea ice, and massive wildfires. We need to, and we can break the climate loop by using ICE 911 solutions. Thank you.